Hello everyone, this is Professor Roman. Let's continue the field theory lectures. I want to talk now about roots of unity and binomials. This is the last stepping point to our discussion of solvability by radicals in the next chapter. Now, first of all, to avoid some, let's say, distracting complications, I'm going to assume that all fields have characteristic 0. I was torn as to whether to make this assumption or not, quite frankly. I could relax this restriction, but not completely, because if you allow fields of prime characteristic, life can get very much more complicated. There is an intermediate step that I could have taken. The discussion we're going to have in this chapter would apply equally to fields of prime characteristic, say P, provided that when we talk about nth roots of unity, P does not divide n. When we talk about binomials of the form x to the n minus u, P does not divide that exponent n. When we talk about nth root extensions, P does not divide that n. So, as you can see, it becomes a little bit complicated. So I just decided that the best course of action will be to assume that all fields have characteristic 0. Okay, so roots of unity. Let F be a field, and I hope this is the last time I'll say of characteristic 0. The roots in F bar, algebraic closure of F, of this binomial x to the n minus 1 are referred to as the nth roots of unity over F in F bar. And the common symbol for this, I think, at least what we're going to use, is U sub n. And I'm also going to let E sub n be a splitting field for this binomial in F bar. The set UN of nth roots of unity over F is a cyclic group of order n under multiplication. Moreover, if m and n are relatively prime, then UMN is equal to UM. This is the symbol for the internal direct product of UM and UN. It's the symbol I used in the group theory course. It's my own symbol. I've used it in the past, but you probably won't see it anywhere else. So what it means is that UMN is the set product of UM and UN, and UM and UN are essentially disjoint. In other words, their intersection is trivial. As to proof, if alpha and beta are nth roots of unity, then so is the product. That's pretty clear. And so UN is a finite subgroup of this multiplicative group En star. En, remember, is the symbol we're using for a splitting field for the binomial x to the n minus 1. And so we had a theorem back in chapter 1 that told us then that UN is cyclic. Moreover, because the characteristic of F is 0, by assumption, taking the derivative of x to the n minus 1 gives us nx to the n minus 1, and that's non-zero because n is non-zero. So another theorem in chapter 1 tells us that this polynomial x to the n minus 1 has n distinct roots. And here is probably the clearest indication of where things can go differently if the characteristic of the field is a prime p, because if p divides n, then this derivative is 0, and in fact, this polynomial will have multiple roots. And that has a profound effect on the way things go. For the second part of this theorem, suppose that alpha belongs to both um and un. That means it's an mth root of unity and an nth root of unity. And so alpha to the m is equal to 1, and that's equal to alpha to the n. And since m and n are relatively prime by assumption, we can apply Bezo's identity. There are integers a and b for which am plus bn is 1. So alpha is alpha to the am plus bn, which looks like this, which is 1. And that shows that um and un are essentially disjoint. So the mn products in this set product here, which is a group, un, the set of all products of an element from um and an element from un, these are all these products are distinct. And since this set product is a subgroup of umn, it follows that they are equal. The generators of this cyclic group un have a special name. An element omega in un of order n, that is to say a generator of this cyclic group, is called a primitive nth root of unity over f. And I'm going to denote the set of all primitive nth roots of unity by capital Omega sub n. Now, maybe a little bell is going off in your head saying, well, wait a minute, we already have a definition of primitive element, and that's true. So, unfortunately, the term primitive is used in two different senses, a group theoretic sense and a field theoretic sense, and we're kind of stuck with that. But a primitive nth root of unity, which denote here by omega sub n, being a group primitive element is also a field primitive element because the powers of omega sub n generate un. So when we adjoin a primitive group theoretical primitive nth root of unity to f, it's equivalent to adjoining all the roots of unity, the nth roots, and so we get the splitting field. So omega n is field primitive as well as group primitive. But it doesn't work the other way. En will have field primitive elements that are not group primitive. They may need addition in order to generate the field. Okay, so if omega is a primitive nth root of unity, then all of the primitive nth roots of unity are formed by taking powers of omega where the exponent is relatively prime to n. So this is a more concise way to say it. The set of primitive nth roots of unity is the set of omega to the k, where k belongs to zn star. So this is exactly the integers in zn that are relatively prime to n. So the size then of omega sub n, the number of primitive nth roots of unity, is phi of n, where phi is the Euler-Totient function. And if m and n are relatively prime, we have a similar formula here. omega sub mn is omega m times omega n. As to proof, for the first statement, since the order of omega as a group element is n, we have this formula which comes from, we discussed it at length in the group theory lectures, the formula for the order of a power of an element. It looks like this. It's n divided by the GCD of n and k. Well, that's equal to n if and only if n and k are relatively prime. So omega to the k is a primitive nth root of unity if and only if n and k are relatively prime. As to the final statement here, well, since un is an abelian group and m and n are relatively prime, the order of a product of a primitive mth root of unity and a primitive nth root of unity is the least common multiple of the orders of the individual factors, and that is n times m. And so this set product is contained in omega mn. But the products in un we've already discussed are distinct, and so are these products, therefore. And so the size of this set product is phi of m times phi of n, which is phi of mn. This is a property of the totient function, and that's the size of omega mn. So the inclusion and the fact they have the same sizes means they're equal. The term cyclotomy refers to the process of dividing a circle into equal parts. And that's precisely the effect obtained by plotting the nth roots of unity over the rationals in the complex plane. So this is an example here of plotting the seventh roots of unity, these points here. And that divides the circle into 7 equal arcs. So, definition. Suppose that omega is a primitive nth root of unity. The splitting field, F with omega adjoined, for this binomial is called a cyclotomic extension of F. And so, I guess I didn't say it, but I should probably have done so. So we'll refer to this as a cyclotomic extension. F with omega joined is a cyclotomic extension of F, or you could say this extension is cyclotomic. And we will refer to n as the exponent of the extension. Theorem, let F be a field and let omega be a primitive nth root of unity. Then this cyclotomic extension is Galois. It's normal and it's separable. And so the size of the Galois group of the extension is equal to the degree of the extension. This En is F with omega adjoined, and that's the degree of the minimal polynomial of omega over F. This, by the way, does depend on the separability. So we're, because we're assuming all fields have characteristic 0, all extensions are separable. So this is a normal extension in any case because it's a splitting field extension, but to for it to be Galois, it needs to be separable as well. It would be separable, by the way, if the field F, and therefore any extensions, have prime characteristic P, provided P does not divide N. Now, just to be clear, the order of a primitive nth root of unity as an element of the group UN is n. Omega has order n as a group element. But the degree of omega over F, that's different. That, as we're going to see, that degree divides phi of n. And so it is less than n. So the field degree of a primitive nth root of unity is smaller than the group order of that element. And it wouldn't surprise me if you want to pause the video for a minute and kind of let that sink in. In any case, as to the Galois group of this splitting field for the nth roots of unity, if sigma is a member of the Galois group, it's uniquely determined by its value on omega. And since sigma preserves order, and this is group order, it follows that sigma omega has to be one of these phi of n primitive nth roots of unity. So sigma applied to omega has to be omega to, let's say, the k sub sigma power. And k sub sigma belongs to Zn star. These are the units of Zn. So k sigma, the exponent, completely determines sigma. And that leads us to define a function from the Galois group to Zn star. I called it kappa. Kappa of sigma is this exponent, k sub sigma. Also, since we have omega to the k sigma tau is sigma tau applied to omega, so sigma and tau both belong to the Galois group. I should have said that, since for sigma and tau in the Galois group. Okay, I'll fix that. So this is sigma tau of omega, which is sigma of omega to the k tau, which is sigma omega raised to the k tau, which is omega to the k sigma k tau. What we get here is that kappa preserves multiplication in the Galois group. So it's a group homomorphism. And since k sigma is equal to 1 if and only if sigma is the identity, if and only if sigma sends omega to itself, and that means it's the identity, kappa is injective. So it is a group embedding, which means that the Galois group is isomorphic to a subgroup of Zn star. Well, it might also seem like kappa ought to be surjective as well as injective, but that's not true. And the reason is that this polynomial, which is the product of these linear factors, x minus omega to the k, where k belongs to Zn star, that's this guy here, okay. The roots of this polynomial are precisely the primitive nth roots of unity. This doesn't have to be irreducible over f. If it was irreducible, it would be the minimal polynomial of omega. But that's not necessarily true. And so there need not be a member of the Galois group that sends omega to the k for all possible k. So that means that kappa would fail to be surjective. Okay. And I'm going to have more to say about the irreducibility of these kind of polynomials shortly. So in summary, if we have a cyclotomic extension with exponent n, so En is the splitting field for x to the n minus 1 over f, then its Galois group is isomorphic to a subgroup of Zn star. That means the Galois group is abelian, because Zn star is abelian as a multiplicative group. And so the cyclotomic extension is an abelian extension. And the Galois group has the same size as the degree of the extension, because this is a finite Galois extension, and that's going to therefore divide the order of Zn star, which is phi of n. And that's what I promised earlier. Okay. So this tells us again that the degree of omega, a primitive nth root of unity, which is this degree, divides phi of n, whereas the order of omega is by definition n. To investigate the properties of cyclotomic extensions further, we're going to factor x to the n minus 1. Now, since each root of this polynomial is a primitive dth root of unity for some d dividing n, if each root is an nth root of unity, which makes it a primitive dth root of unity for some d dividing n, we're going to define what is called the dth cyclotomic polynomial, q sub d of x, to be the polynomial whose roots are precisely the phi of d primitive dth roots of unity. So, if omega sub d is a primitive dth root of unity, then the dth cyclotomic polynomial is this product. Product of linear factors omega sub d to the power k, where k is in zd star. We saw this polynomial a few minutes ago when I discussed the fact that it might not be irreducible. So the degree of qd is phi of d, and we also see that if we take the product of all these cyclotomic polynomials of degree d dividing n, we get a polynomial that's monic and whose roots are the same as the roots of x to the n minus 1. We just are grouping them by their order, by their group order. And so we have this equation. Theorem. In summary, let Qn of x be the nth cyclotomic polynomial. Its degree is phi of n. We have this product formula, which we will see in a minute is extremely useful in computing cyclotomic polynomials. You might think that should be a daunting task because you have to find all the elements of a certain order within a group, but it's actually quite easy from this product. Qn of x is monic and has coefficients in the prime subfield of f. As a matter of fact, when f, the base field, is the rationals, the coefficients of Qn of x are integers. So So we've already discussed these first two. So we'll go to 3 and 4 here. And they can be proved at the same time by induction on n using this formula. So in particular, suppose that f prime is the prime subfield of f. Then it's clear from the definition that these are monic. Okay, so that's no big deal. Q1 of x is x minus 1. And so the results here in 3 and 4 are true for n equals 1. If n is a prime p, then this formula, there's not much in the way of divisors of p. X to the p minus 1 is then q1 of x times qp of x, which is x minus 1 times qp of x. So qp of x is this sum here, this polynomial. And that certainly has coefficients in the prime subfield and integer coefficients as well. So 3 and 4 hold for n equals p prime. So now let's assume that 3 and 4 hold for all proper divisors of n. Then x to the n minus 1 is qn of x times the product of the other qd's, where, again, d divides n, but now d is less than n. And that's qn of x, let's call that r of x. And by the induction hypothesis, r of x has coefficients in f prime, and therefore so does qn of x. Moreover, if f is the rational field, then r of x has integer coefficients. Since it's monic, it's primitive, and there's another use of the term primitive polynomial, and it follows then that qn of x has integer coefficients. This is a little bit of ring theory we discussed in that course concerning polynomials over a ring, over a unique factorization domain, and so on. Now, this formula here can be written in this form. So qn of x is x to the n minus 1 divided by the product of the qd's, where d divides n but is less than n. And this formula, together with the fact that q1 of x is x minus 1 and qp of x is equal to this, we can use this formula then to compute cyclotomic polynomials of any size we want. So, for example, q4 of x is x to the 4th minus 1 divided by q1x, q2 of x, because 1 and 2 are the divisors of 4 that are less than 4. And these are here, and so we get x squared plus 1. q6 of x is x to the 6th minus 1 over q1, q2, q3, and that works out here. q15 of x, I'll let you work out some of these if you wish. So actually these are enough to give us a factorization of x to the 15 minus 1 into cyclotomic polynomials. So I'll let you work that out. Okay. So in any case, the theorem, let me go back here. So the formula here gives us this factorization, which is a factorization of x to the n minus 1 within the prime subfield of f, because these polynomials have coefficients in that subfield. But it's not necessarily a prime factorization, of x to the n minus 1. The coefficients are in the prime subfield, but that's got nothing to do with whether this is a prime factorization. In fact, it doesn't have to be because, as I said before, the cyclotomic polynomials are not necessarily irreducible. Here's a simple example. If we take the field Q with square root of 2 adjoined, Q8 of x, and I'll let you work this out, comes out to x to the 4th plus 1, and that factors this way. So Q8 of x is reducible over this base field. Now you might wonder why I didn't find an example where f is q, and the reason is there is none, because we're going to show next, actually, that all cyclotomic polynomials over the rational field are irreducible. So we've seen then that for a cyclotomic extension of order n, so omega is a primitive nth root of unity, the Galois group is isomorphic to a subgroup of Zn star, which and has order phi of n. This group has order phi of n. So the Galois group is isomorphic to the full group Zn star if and only if the degree of omega, which is the degree of its minimal polynomial, is phi of n. But omega is a root of this cyclotomic polynomial, which has degree phi of n. So if Qn of x is not irreducible, then omega will have smaller degree than phi of n. Okay. So the Galois group is isomorphic to the full group if and only if Qn of x is irreducible, making it the minimal polynomial of omega, and thereby giving omega degree phi of n. So, theorem. Have a cyclotomic extension for this binomial. The Galois group is isomorphic to Zn star if and only if the nth cyclotomic polynomial is irreducible, in which case it is the minimal polynomial. Well, as I said before, all cyclotomic polynomials over the rational field are irreducible over Q. And so when we have a cyclotomic extension over Q, its Galois group will be the full group Zn star and will therefore have degree phi of n. And here's the proof. It's a very interesting proof. Not something you might think of right off, or even a little later than right off. Suppose that f of x is an irreducible factor of Qn of x. So Qn of x is f of x, g of x. And both factors are monic with integer coefficients. So to show that Qn of x is irreducible, we have to show that g of x is constant. Well, let's take an omega in a primitive nth root of unity that's a root of f of x. Okay. What we're going to show is that omega to the pth power is also a root of f of x for any prime p that does not divide n. Once we do that, then if q is also a prime that does not divide n, we can apply the same argument again, and omega to the pq, we'll apply it this time to omega to the p, showing that omega to the pq is also a root of f of x. And from that it follows that for any integer k relatively prime to n, omega to the k is a root of f of x. So all roots of qn of x are roots of f of x. And that doesn't leave any room for g of x. So g of x is 1, f of x is qn of x, and qn of x is irreducible. Okay? So we want to show then that omega to the p is a root of f of x. If it's not a root of f of x, it's got to be a root of g of x. And therefore omega is a root of this polynomial, g of x to the p. And that implies that f of x divides g of x to the p. F of x is assumed to be irreducible, an irreducible factor. It has root omega, which makes it the minimal polynomial for omega. And so it divides any polynomial that has omega as a root. So g of x to the p looks like h of x, f of x, where h of x is monic with integer coefficients. Now, since Fermat's little theorem says that a to the p is congruent to a mod p for any integer a, we have g of x to the p. There's not much we can do with this, so we're going to say this is congruent to g of x to the p mod p. So now we take residues mod p, okay, which I'll denote with overbars. So g bar of x to the p is h bar f bar. And these are now polynomials in ZP, square bracket x. So, because of this relationship, f bar and g bar must have a common root in an appropriate extension of ZP, in a splitting field, let's say, for all these polynomials. Okay. But f bar g bar divides qn bar, which divides x to the n minus 1 bar. We're now dealing with polynomials in ZP. So this is division over ZP square bracket x. But this guy has no multiple roots in any extension of ZP. But what we just got through saying was that f and g have a common root, which would be a multiple root of x to the n minus 1 bar. So there's the contradiction. And it implies that omega to the p is a root of f of x. And from what we said before, that completes the proof. Let's now examine more general binomials, x to the n minus u, where u lies in the base field f. So let f be a field, a polynomial of the form x to the n minus u, where u is non-zero and lies in the base field, is called a binomial over f. Suppose that alpha is a root of this binomial x to the n minus u in some splitting field S. Then the complete root set for this binomial in the splitting field is alpha omega alpha, omega squared alpha, up to omega to the n minus 1 alpha, where omega is a primitive nth root of unity. And since the splitting field is f with the roots adjoined, that's the same as f with omega and alpha adjoined. Because if you have omega and alpha, you have all of the roots. And if you have all of the roots, you have alpha and omega alpha, therefore you have omega. So that's why this equality holds. So it follows then that this is in fact the splitting field for this binomial. So let f be a field, again, characteristic 0 by assumption. P of x is a binomial with root alpha in some extension f bar. Then for any omega primitive nth root of unity, this extension is a splitting field for the binomial, and when the nth roots of unity lie in the base field, then all we have to do is adjoin a single root alpha to get a splitting field. Before we continue, let me repeat here an earlier definition. And to be honest with you, I can't remember if in the video, when I first mentioned this, I used this precise terminology. I may have worded it somewhat differently, but it doesn't matter. It's all the same. A proper field extension, FE, is an nth root extension or has type n if E is f with alpha adjoined, where alpha does not lie in f, but alpha to the n does lie in f. And we'll also say that alpha is a type n witness for the extension. When we don't care to mention the type, I'll just use the phrase root extension. The main issue that concerns us here is to determine the relationship, if any, between root extensions and cyclic extensions. So, are root extensions cyclic? Are cyclic extensions root extensions? Well, the answer is it depends upon the location of the relevant roots of unity. So let's first consider an nth root extension, FE. E is generated by a witness alpha, so alpha to the n belongs to the base field. And let's assume that the base field F contains the nth roots of unity. We've seen that F alpha is a splitting field extension for this binomial over F. And so the extension is Galois, because we're assuming all fields have characteristic 0, and so all extensions are separable. This is normal, and therefore also Galois under our assumption. And the Galois group G of this extension is the same as the Galois group of the binomial. As to the Galois group, since each sigma in G is uniquely determined by its value on the generator alpha, and since this value, being a root of the binomial, has to be another root, sigma takes roots to roots, sigma alpha will have this form, omega to the k sub alpha, k sub sigma alpha. Okay. Because the roots of the binomial are all powers of omega times alpha. Omega is a primitive nth root of unity. And this is, k is subscripted by sigma because it depends on sigma. As a matter of fact, this map, that phi that sends the Galois group to the set of roots of unity, this is a cyclic group, defined by phi sigma is omega to the k sigma, this factor here. This is an embedding of the Galois group into the group UN. And here is the demonstration that it's a group homomorphism. I'll let you sort that out. The kernel of phi is trivial because if omega to the k sigma is 1, that means that sigma sends alpha to itself. And so it sends a generator to itself. It's got to be the identity. So the Galois group G is isomorphic to a subgroup of UN. But UN is cyclic. And therefore, the Galois group is cyclic of some order D dividing N. So it has this form where sigma generates the Galois group. So we have made the connection between nth root extensions and cyclic extensions through the Galois group. The Galois group of the binomial, or of the nth root extension, is in fact isomorphic to a subgroup of UN, and UN is cyclic. So that's the connection. So in summary, if UN is contained in the base field, then an nth root extension is cyclic of degree D dividing N. If D is if the extension has degree D, then the Galois group has order D, because we have a Galois extension. Also, the minimal polynomial of alpha over F will have degree D. But notice, sigma to the D is the identity. Sigma has order D. And so alpha, the generator, is sigma to the D alpha, which is omega to the D k sigma alpha. And so omega to the D k sigma is 1. And therefore, sigma applied to alpha to the D, I'll let you go through this, is again alpha to the D. In other words, alpha to the D is fixed by sigma, and therefore it's fixed by the entire Galois group, and so it belongs to the fixed field of the Galois group. But that's F, because the extension is Galois. So alpha to the D also belongs to the base field. We knew that alpha to the N belonged to the base field because the extension was an nth root extension. This tells us that alpha to the D belongs to the base field. Therefore, this extension is also a dth root extension. And since the binomial x to the D minus alpha to the D, now that belongs to F square bracket x, it has degree D, it has root alpha, so it is the minimal polynomial. And you can check for yourself that since D divides N, x to the D minus alpha divides x to the N minus alpha to the N. Did I say that right? X to the D minus alpha to the D divides x to the N minus alpha to the N. And that's because D divides N. So, theorem, just what I've just said, really. Suppose that Fe has degree D greater than or equal to 2, and let N be greater than or equal to 2, then if UN is contained in F, if the base field contains the nth roots of unity, and if Fe is an nth root extension, then D divides N, UD is contained in F, then, because D divides N and because UN is in F, and FE is a cyclic dth root extension. Also, a witness of type N is a witness of type D, so that if alpha generates E over F and alpha to the N is in F, then, well, I'm just repeating here, then alpha to the D is in F and the minimal polynomial is this. If we take N equals D in this conditional statement, then we can say that if UD belongs to the base field, so D is the degree of the extension, if the dth roots of unity belong to the base field, then FE is a dth root extension, implies FE is cyclic. This has a converse. So suppose that UD belongs to F, and that FE is cyclic of degree D. And here is its Galois group. We want to show that FE is a dth root extension. And it will then, by the way, be an nth root extension for any n that's a multiple of D. Well, to do this, we have to find a witness. We have to find an element alpha in E, but not in F, that generates E over F, and for which alpha to the D belongs to F. Well, we can do this if we can find a non-zero alpha in E that for which sigma alpha is omega alpha for a primitive dth root of unity. Then alpha will not be an F because sigma fixes the base field pointwise but does not fix alpha. Also, the minimal polynomial has a complete root set in the splitting field, and it looks like this. You apply alpha as a root, and then you apply the elements of the Galois group to get the other roots, and those are, because we found an alpha for which sigma alpha is omega alpha, the roots look like this. These elements are distinct, and so alpha has degree D, and so it generates E over F. Also, the product of the roots is positive or negative alpha to the D, and that is up to algebraic sign. The constant term of the minimal polynomial, therefore it's in F. So we have a generator of E over F whose dth power lies in the base field, so this is a dth root extension. Excuse me while I have a sip of water. So we're left with finding a non-zero alpha in E for which sigma alpha is omega alpha, or sigma inverse, omega inverse sigma alpha is alpha. We can, since omega is any primitive dth root of unity, so is omega inverse, so we can swap omega inverse, put omega there, and so this is what we're looking for. Omega sigma alpha equals alpha. Alpha must be non-zero. But if for any beta in E, we set alpha sub beta to this, so we are applying this map to beta, identity plus omega sigma all the way up to omega d minus 1 sigma d minus 1. Look what happens when we apply omega sigma. to alpha sub beta. It looks like this. The omega sigma goes inside. It just kind of kicks up the exponents by 1. But omega to the d, sigma to the d, is the identity. So we recover alpha sub beta. And that is then what we are looking for, alpha sub beta, provided it's non-zero. So we're not quite done. But if alpha sub beta were 0 for all choices of beta in E, then this operator here would be the 0 operator, and that contradicts the linear independence of the embeddings identity up to sigma to d minus 1 that's guaranteed by the Dedekind independence theorem. Well, so now we can improve upon the previous theorem, or augment it with this converse. And this gives us the critically important connection between root extensions and cyclic extensions that will be very valuable to us when we talk about solvability by radicals. So the theorem says let Fe have degree d bigger than or equal to 2, and let n be bigger than or equal to 2. First, if we have an extension Fe, an nth root extension, and if un, the nth roots of unity, lie in the base field, then Fe is also a cyclic dth root extension. D is the degree. And n is a multiple of d, and ud also belongs to F. And this is the stuff about witnesses and minimal polynomials I talked about before. Part 2, if ud is in F, so these are the dth roots of unity where d is the degree of the extension, if they belong to the base field, then the following are equivalent. Fe is a dth root extension, Fe is cyclic. Now you might be wondering what to do if the relevant dth roots of unity or nth roots of unity don't lie in the base field. Well, we lift. So theorem 4.5 tells us that root extensions are closed under lifting. And corollary 531 tells us that the property of being cyclic is preserved under lifting. So if the base field F in an extension doesn't contain the relevant roots of unity, say the kth roots of unity, then we can lift the extension by any primitive kth root of unity, and then this theorem will apply to the lifted extension. And this is exactly what we're going to do in the next chapter on solvability by radicals. Finally, I have included in the book a discussion of how to determine the Galois group of a binomial when the roots of unity are not in the base field. It's not terribly difficult, and it's pretty interesting, but it's not really relevant to our most important discussion, which is that of solvability by radicals, that occupies the next chapter. So I'm not going to cover this in the video. If you have the book, of course, you can read it. It's just 2 pages, I think.